Welcome back to the deep dive. Today we're taking on a massive and frankly critical challenge: decoding the invisible architecture that controls pretty much every modern digital organization.
We're talking about cloud security.
Exactly. And specifically, the foundational domain that makes security teams sweat: identity and access management, or, IAM.
It's the domain where jargon goes to multiply, absolutely. For a lot of people, starting down the path of cloud security governance feels like being handed a complex blueprint for this massive, heavily guarded fortress where half the labels are just missing.
It's overwhelming.
Totally. And that initial confusion, it often prevents people from getting genuine control over their digital assets.
Right. And because this is often the first real foray into the deep unknown of cloud security for so many people and organizations, our mission today is to just cut through that complexity.
We want to give you a map.
Yes, a comprehensive, crystal clear map focused solely on the identity and security section of cloud governance. We're giving you the shortcut to understanding the who, what, and where of cloud control.
And we're really focusing on that core principle, the controls that dictate who can access your digital assets, and crucially, what they're allowed to do with them.
So the goal is you can leave this deep dive and be able to talk fluently about why your organization uses folders, or why a robot identity has to be treated differently from a human one.
And why things like advanced perimeter controls are so necessary, even if you think you have perfect IAM policies in place.
And this all comes back to a universal principle, a guiding principle for every single access decision in the cloud. We call it the IAM core analysis.
It's really the simplest way to boil down the entire security domain. Identity and access management is built on the foundation of who can do what on which resource.
I love that. It immediately gives us our navigational map. The who is the person or maybe the application trying to get access.
Right.
The what defines the specific actions they can take. And the which resource is the digital asset they're trying to touch, whether that's a database, a VM, a storage bucket, whatever.
And we have to start with the foundation. I mean, before we can even talk about the identities or the permissions, we have to establish the playing field. We have to define the digital real estate itself, the which resource.
Okay, let's unpack this then. So understanding the resource hierarchy is step one in security. You have to know where your assets live, how they're organized, before you can even think about securing them.
Exactly.
So what does this digital real estate actually look like structurally?
Well, it's not a flat landscape. It's a meticulously structured, nested hierarchy. The best way to think of it is like a giant, high-security digital filing system.
Okay.
And this organizational structure, it's defined specifically to allow policies to flow and be managed centrally.
And we begin at the very top, the ultimate umbrella, which is the organization.
Yes, the organization is the legal entity. It is the company name.
Yeah.
Every single asset, every folder, every project, it all has to report up to this single entity.
And this top tier is where you set the broadest rules.
The broadest, most foundational guardrails for the entire corporation. If you define a policy here, you are defining the rule for everyone, everywhere, no exceptions.
Okay, so below that top-level entity, we need a way to group things logically, right? To separate different business units or environments.
And that's where the folder comes in.
Right, the folder.
Folders are absolutely critical. They're the real organizational backbone. They're the logical subdivisions for departments like marketing or finance, or for environments like development and production.
And their main job is to let you apply specific policies to just that group.
That's their primary operational purpose, yeah. It lets you set specific, detailed IAM policies that apply to that section of the business without messing with the policies of another section.
So it sounds like the folder is what prevents policy chaos. Without it, if the finance department needed some strict new security rule, I'd have to apply it manually to every single one of their projects.
And if they spun up a new project tomorrow,
I'd have to remember to do it again, which I wouldn't.
Exactly. The folder level is the governance translation layer. It translates your company's org chart and your business needs directly into technical access rules.
And below the folder, we hit the true operational unit, the project.
The project is where the work actually gets done. Think of a project as a dedicated workspace for a specific application or a team function. It's the primary container for all your resources.
And it does more than just contain things.
Oh, yeah. Crucially, the project establishes boundaries for billing, for quotas, and it's the default boundary for network isolation. So when you build your new mobile API, it lives in a project. Your big data pipeline, a different project.
Got it. And finally, inside that project, we have the granular items, the assets we're ultimately trying to protect, the resources.
Right. Resources are the individual components, the VMs, the databases, the managed services, the storage buckets, the load balancers, the actual stuff.
So understanding that nested relationship organization, to folders, to projects, to resources, is the absolute foundation for security planning.
It's everything.
Okay, now that we've mapped the digital real estate, let's get into the complexity that you mentioned, the flow of rules. If I set one set of rules at the organization level and then a completely different set of rules lower down, say on a project,
Yeah.
which one wins?
And this is the crucial rule of inheritance. It fundamentally alters how security teams have to approach their initial policy grants. The effective policy at any level, folder, project, or resource, is not an override. It is the union of the policy set directly at that node, and every policy inherited from its ancestors.
The union. Okay, so put that another way. Permissions are always additive as you move down the hierarchy.
Always additive.
So if I have permission for my organization and a separate specific permission for my project, I get both of them combined.
That's the gravity of the rule. If you grant someone, say, the powerful project editor role at the organization level, you cannot, later on, try to restrict them at the project level by just applying the project viewer role.
Because it doesn't subtract.
It doesn't subtract or override. The permissions only aggregate. The user gets both editor and viewer, which means they're still an editor.
That realization is so critical because it forces security teams to be restrictive at the top. You have to start with least privilege.
You have to. Let's trace that principle through a really common practice, managing distinct environments like development and production.
Okay.
When you're dealing with these, the goal is policy separation while, maintaining central management. The recommended approach is to create two distinct folders, development and production, directly under the organization.
And then at the org level, you set really basic permissions for everyone.
Exactly. Maybe some basic network viewer or logging writer roles, the really restrictive foundational stuff. And then the specialized policies, they're set directly on the respective folder.
So you might grant more liberal roles to the development team, but only on the development folder.
Right. And the tighter security controls, higher encryption standards, more restrictive IAM permissions, all of that is applied only to the production folder.
So the benefit isn't just about initial organization, it's about agility. If the business decides we need a new global monitoring policy, I can apply it once at the top at the organization level.
And both development and production instantly inherit it.
But when I need to tighten a specific production policy, say block external APIs, I can do that just on the production folder without ever disrupting the developers working in their, liberal development sandbox.
Precisely. It gives you independent central control. Now let's use the finance folder case to really illustrate the operational danger of this additive-only union rule.
Yeah.
This is a common failure point I've seen a lot.
Okay, walk us through the setup for this high-risk scenario.
We have a company, they've got a sensitive finance folder, and another one, let's call it shopping. The development team, maybe as a quick fix months ago, was granted the powerful project owner role at the very top, the organization level.
Which is basically the keys to the entire digital kingdom.
Essentially, yes. Now, the security goal is to prevent that development team from creating resources like VMs or storage buckets in the projects that live inside that finance folder.
Okay, so security realizes their mistake, and they try to fix it by applying a weaker role. Let's say they assign the development team the less powerful project viewer role, but only on the finance folder. What happens?
Nothing. Well, nothing good. Because of the union rule, the project viewer role is just added to the project owner role they already inherited from the organization.
They still have owner privileges.
They still have owner privileges, and they still have full control over the finance projects. The new, weaker policy is effectively ignored. And this isn't just a technical detail, it's a source of massive organizational friction because the security control you thought you put in place completely fails.
That's the aha moment that hits security teams hard. The only way to fix this security loophole isn't to add a weaker role lower down, but to perform surgery at the top.
Absolutely. The only secure remedy is to acknowledge the flawed initial design and remove the overly broad project owner role from the organization entirely. You have to pull back those massive permissions at the highest possible level.
And then you adhere to the principle of least privilege by what? Granting it back, but more specifically.
By assigning them project owner roles selectively, only on the specific folders or projects they absolutely need to administer, so maybe only on the shopping folder, or a dedicated development folder. It just illustrates that broad roles at the organization level are organizational risk amplifiers.
And cleaning up that policy sprawl is always exponentially harder than granting permissions correctly the first time.
Always.
Okay, the which resource is clear. We understand the landscape, the flow of inheritance. Now let's shift to the who and the what. Who is accessing the environment and what key are they carrying? This brings us to the core definition of IAM roles.
So IAM roles define they're the set of atomic permissions that determine what actions an identity can take. They are the keys. And in the cloud, roles fall into two main camps, mostly based on their scope and how old they are.
Let's start with the historical ones, the ones that security teams are, actively trying to move away from, the primitive roles.
These are the old master keys,
Yeah.
owner, editor, and viewer. They are extremely broad. They grant hundreds of actions across dozens of services. They were convenient early on, but they completely violate the principle of least privilege.
Because if an identity with the editor role gets compromised,
The entire project, and potentially everything beneath that project in the hierarchy, is at risk. That is a massive blast radius.
so the modern security-conscious shift is toward granularity, which means adopting predefined roles.
Correct. Predefined roles are narrowly tailored. So instead of giving you the master key, the editor role, they give you only the key for the server room door. That would be compute admin, or just the key for the filing cabinet, which is storage object creator.
Yeah. And that means if that one identity is compromised, the attacker can only do the specific limited tasks defined by that role.
Exactly. It dramatically reduces the blast radius of any security incident.
Okay, that makes sense for human employees. But you mentioned the who also includes machines. Can you expand on the difference between a user and a service account?
This is a fundamental concept for anyone new to cloud security. A service account is a non-human identity. It's an ID created specifically for a robot, an application, or an infrastructure component that needs to perform actions autonomously without a human logging in.
The robot analogy is really helpful for defining the purpose, but operationally, why do service accounts introduce their own unique security challenge?
Well, they're crucial for automation. Imagine a cron job that backs up your database every night, or a virtual machine running a microservice that needs to read configuration files from a secured bucket.
The application on the VM needs permissions to read the bucket.
Right, so you attach a service account to that VM. The service account's permissions are what the application inherits, allowing it to do its job without embedding static, human-provided passwords in the code.
And the challenge?
The challenge is that since they are non-human, they lack things like multi-factor authentication and the behavioral protections we apply to human users. If an attacker gets control of a service account's token, they become the robot.
Which emphasizes why granting least privilege is arguably even more critical for service accounts than for human users.
Okay, focusing back on human identities. What if a startup is born in the cloud, meaning they never had any legacy systems? How do they handle user management?
If you're cloud native, the central service for identity management is Cloud Identity or, Google Workspace. This becomes your authoritative source for all user accounts, groups, and provisioning. It's the backbone. And if they use Cloud Identity, they get immediate benefits beyond just basic login.
Oh, absolutely. Cloud Identity enables robust password policies, centralized user lifecycle management. So when a user leaves, you disable them at one place. And crucially, it enables single sign-on, or SSO.
So one login for everything.
One corporate identity to log into all their cloud resources and their third-party SaaS apps like Salesforce, Slack, or GitHub. It simplifies the user experience and dramatically improves security hygiene.
That successfully centralizes authentication control. But what about the legacy organizations? The companies that have thousands of users already define an on-premises Active Directory. They don't want to move their entire identity system to the cloud.
They have to federate their identity. The recommended solution for retaining on-prem Active Directory is not to sync passwords or use brittle API calls. It's to use Google Cloud Directory Sync to synchronize group memberships and usernames, just the directory info with the cloud system.
Okay.
And then they must configure SAML SSO, which is federated authentication, to connect to their existing identity provider.
Why is that SAML SSO piece non-negotiable for security?
Because federation preserves the security control of the domain controller. When a user tries to access a cloud resource, the cloud environment redirects them to the company's internal identity provider, or IDP. The user enters their corporate password only on the secure, trusted on-premises Active Directory.
So the cloud never sees the password.
Never. The IDP sends back a signed token, the SAML assertion, which proves the user's identity to the cloud. The key point is the cloud never sees or stores the corporate password, which significantly lowers the risk profile.
That's a massive security win. You're preserving the existing control plane while granting access to the cloud. Now, let's talk about operational maintenance. For large teams, granting permissions to 50 individual users in a project is a nightmare.
It's disaster.
What's the scalable, low-maintenance strategy for granting access to an entire department?
We leverage the efficiency we've built into both sides of the equation, the identity side and the resource side. It's a three-step strategy for minimal maintenance.
Okay, what is it?
First, create a Google group per department and add all the human members to it. Second, create a folder per department in your resource hierarchy. And third, grant the required IAM permissions to the group at the folder level.
Let's trace the efficiency game here. Why does that structure save so much maintenance time?
Well, when a new engineer joins the team, the only administrative action required is adding their user ID to the engineering Google group. They instantly inherit all the necessary permissions for the engineering folder and, by extension, every single project inside it.
And the other way around.
Yeah.
A new project.
If a new project is created, you just place it under the correct department's folder. It automatically inherits the correct group permissions for the entire team instantly. You only manage group memory and folder placement, not thousands of individual user permissions. It's so much cleaner.
Okay, that covers the who, the what, and the where.
Yeah.
We've established how permissions are structured, but as we know from the security world, perfect access control just isn't enough. We need to enforce boundaries. This takes us to the advanced controls designed to enforce the concept of zero trust.
Zero trust is fundamental. The underlying shift is abandoning trust based on network location. The motto is, verify every request, assume no network is safe. It's about moving beyond that traditional network firewall approach.
So we need tools that check not just who you are, but where you are and what device you are using for every single connection, even if you're accessing internal resources.
Right. And the primary service that acts as the policy enforcement point for zero trust in the cloud is the Identity-Aware Proxy, or IAP. IAP is essentially a virtual front door to your internal web applications. It completely bypasses traditional VPN access by checking identity and context before it grants access to anything.
Okay, let's run an advanced scenario that really shows the power of IAP when you combine it with those contextual checks. Let's say we have a highly sensitive internal analytics dashboard.
Okay.
We want to grant access only to employees who are using a corporate managed device, and they must be physically located inside the headquarters office. How do we build that complex rule?
The solution is the combination of Identity-Aware Proxy, IAP, combined with access levels, which are defined through the Access Context Manager.
So two pieces.
Two pieces working together. IAP handles the identity check, making sure the user is who they claim to be. The access levels define the granular contextual conditions. So you define an access level that mandates two criteria. The user must have an accepted device status, so a corporate device that is encrypted and patched, and choose. They must originate from the trusted IP range of the headquarters office.
So the security check is layered. If the user successfully authenticates, that's the who IAP, then checks the policy from the access level, which is the context.
Right.
And if they're using a personal laptop or connecting from a coffee shop, even if they have perfect IAM permissions, the connection is blocked at that virtual door.
Correct. It creates a dynamic, context-based security policy that follows the user, not the network perimeter. And that is the core of zero trust.
So IAP handles the front door to applications. But what if the data itself, the contents of our BigQuery databases or cloud storage buckets, is at risk of being copied out by an employee who already has perfectly valid IAM permissions?
That's when you need the ultimate boundary enforcement mechanism, VPC service controls. I call it the ultimate moat.
The ultimate moat. I like that.
This technology is deployed when the risk of data exfiltration data being stolen by moving it outside your defined network is the paramount concern. IAM is about granting access. VPC service controls is about enforcing the boundary of the data itself.
The moat analogy is incredibly effective here. It creates a hard security perimeter around the cloud-managed services where your sensitive data lives. What's the primary classic use case this solves?
Use case 1, preventing exfiltration. So consider a disgruntled or maybe just a careless employee with the data viewer IAM role on your sensitive BigQuery project. They could write a simple script to copy millions of records to a personal storage bucket they created in a project owned by their personal Gmail account. Since they have valid IAM permission to read the data, IAM alone would permit this.
So how does the moat stop a valid user with valid read permissions from doing that?
You implement a VPC service control service perimeter around your sensitive projects and services, BigQuery, cloud storage, and so on. This perimeter acts as a non-negotiable boundary. It dictates that once data is inside, API communication regarding that data can only happen with other resources that are also inside the perimeter.
So if the user tries to issue the API command to copy data from the sensitive BigQuery project to any resource outside the perimeter,
The VPC service controls layer intercepts the API call and explicitly denies it. It doesn't matter what the user's IAM role is. The copy operation fails.
that is a critical layer. It enforces a compliance boundary that IAM just can't touch. But this kind of hard boundary, it often causes operational pain, right? If VPC service controls overrides IAM, what's the primary challenge that security and development teams run into when they first implement the moat?
That is an excellent question, and it's a huge source of friction. The main challenge is troubleshooting cross-boundary calls. Because the perimeter is so strict, when an application inside the moat tries to interact with a seemingly internal service outside the moat, maybe legitimate external analytics tool or a common API, the request is just silently blocked by the perimeter.
And developers get these cryptic, permission-denied errors that look like IAM failures.
But the issue is actually the network boundary enforcement. It requires meticulous planning and often the use of things like egress rules or bridge projects to allow controlled, audited traffic to cross the boundary, which, it complicates the architecture.
That confirms that while the moat is the ultimate security tool, it has to be planned with precision. Okay, let's move to a scenario that combines the moat with the identity context. Use case 2, restricting network origin.
So the goal here is to ensure that data analysts can only retrieve data from sensitive cloud storage buckets when they are inside the trusted Office network. If they go home, their access should be denied, even if they're using a corporate device.
We've already covered the tools for context. How do we stack them up here?
You combine the tools we just discussed. First, you secure the data boundary by implementing the VPC service controls perimeter around the project containing the sensitive storage buckets.
Okay.
Second, you define an access level based on the Office network's external CIDR, the IP range. And finally, you attach this access level directly to the service perimeter.
So the access flow is perfectly enforced. The user authenticates, that's the IAM check. They try to read the data. VPC service controls checks the request origin against the attached access level.
And if the API call does not originate from the trusted Office IP, the perimeter blocks the request. The data never leaves the controlled boundary unless the user meets both the identity and the geographic or network context requirements.
Precisely. It's security by policy, enforced by context.
Yep.
We've talked about internal control, but modern environments rely on complex supply chains. What if we have an application running on a completely different cloud, say AWS, and it needs to access our data services, like BigQuery? How do we securely establish that cross-cloud trust?
Historically, this was a disaster waiting to happen. The old method involved creating a long-lived Google Service Account key, a JSON file, and embedding that secret key into the application running on AWS.
Which gives the AWS app permanent, powerful access.
Exactly. And the security team was then responsible for rotating and managing that static, highly sensitive secret across multiple cloud environments, which it almost never happens reliably.
And long-lived keys are always the weakest link.
Always. The modern zero-trust solution is workload identity federation. This technology allows the external workload, the AWS application, to temporarily assume a Google Cloud identity without ever managing or storing secret keys.
This sounds transformative. Can you walk us through the technical flow of how this keyless trust relationship is actually established?
It works based on identity provider trust. So first, you configure a workload identity pool in Google Cloud, and you tell it to trust the AWS identity provider, the IDP URL.
Okay, so you're setting up a trust relationship.
Exactly. Second, when the AWS application needs to access BigQuery, it first asks the AWS identity provider for a short-lived token and assertion that proves its specific identity within the AWS environment. So this specific EC2 instance running this specific role.
So the AWS identity is confirmed, but how does Google Cloud accept that?
The AWS application then presents that AWS-issued token to Google Cloud. And because Google Cloud was pre-configured to trust that AWS identity provider's URL, it validates the cryptographic signature on the token.
And once it's validated,
Once validated, Google Cloud issues the workload a second, extremely short-lived token, maybe valid for just an hour, that grants it the permissions of a designated Google service account. The application uses this temporary token to access BigQuery.
and when the token expires, the access is just gone.
Gone, forcing the workload to re-authenticate, which ensures continuous audited control without any static keys.
That not only eliminates the need for managing static keys, but enforces the principle of something short-lived you can prove you possess. It's a huge shift in managing cross-cloud risk.
It's a game changer.
We've built the security architecture from the ground up. The resource hierarchy, the identities, and the zero-trust perimeter. Now we need to slow down and shift our focus to protecting the actual payload. This is the domain of data sanitization, key management, and meeting regulatory demands.
And let's start with a crucial set of tools for organizations dealing with high volumes of, personally identifiable information, PII, and financial data. Cloud data loss prevention, or Cloud DLP.
Okay, DLP.
DLP's core function is intelligence identifying sensitive information, and then action applying sophisticated techniques to mitigate exposure.
Let's dedicate some time to two critical scenarios for sensitive data handling, because the choice really depends on the business requirement for reversibility.
Exactly. Let's take scenario 1, full removal or redaction. We're ingesting large data sets from external partners, and our legal requirement is that we cannot permanently store any PII, data names, addresses, social security numbers whatsoever. We want it gone forever before it hits persistent storage.
What's the definitive permanent removal tool here?
You have to integrate the Cloud DLP API to redact the PII as part of your data ingestion pipeline, typically using a service like Dataflow. The DLP API scans the stream of data, it identifies PII based on built-in detectors, and it replaces that sensitive data with a generic placeholder or just completely removes the field.
So only the clean, non-PII data gets stored in BigQuery.
And this is permanent, non-reversible removal.
Okay. Now, scenario 2 is significantly more complex. Masking for later re-identification. We're ingesting customer support logs containing highly sensitive data like credit card numbers. We need to mask this data to minimize risk for the analytics teams, but we have to retain the ability to reverse the masking later if required by, say, a court order.
Right. Since the data must be reversible, redaction is out. The solution here is using Cloud DLP to tokenize the data with a cryptographic key. Tokenize or de-identify.
And tokenization replaces the sensitive data with a safe surrogate value, the token.
Exactly. DLP uses a method often involving format-preserving encryption, or FPE. The original credit card number, for instance, is mathematically transformed using a secured cryptographic key into a randomized value that looks like a credit card number but is worthless to a thief.
So for 99% of your analysts, they just use this token for tracking and analysis.
Right. The original sensitive data never leaves the DLP service without protection.
And the key to reversibility.
Only the holder of that highly secured, restricted cryptographic key can present the token back to the DLP service and reverse the process back to the original credit card number.
So, to use the simple analogy, if redaction is burning the sensitive document,
tokenization is sealing it in a vault with a complex cipher that only the compliance team holds the key to.
that transition brings us perfectly to the next pillar, the cryptographic infrastructure itself. If we're talking about keys for tokenization or keys for encryption at rest, they have to be managed with extreme care. This moves us to the Key Management Service, or KMS.
KMS is the centralized, highly hardened service for managing the lifecycle of cryptographic keys used across the entire cloud environment. And while a cloud provider generally handles default encryption, many organizations need a higher level of assurance. They want control over the keys themselves.
Let's focus on the highest level of assurance. What if a user requires the absolute highest industry standard for a physical key, something like FIPS 140.2 Level 3, but they don't want the immense headache of purchasing, securing, and maintaining the physical hardware themselves?
They require the security of hardware combined with the operational ease of the cloud. The service for that is Cloud KMS with Hardware Security Module, or HSM. HSM keys are physically backed by dedicated Google-managed hardware security modules that meet that stringent FIPS Level 3 standard.
And what does that FIPS 142 Level 3 certification actually guarantee?
It provides a verifiable guarantee that the key material was generated inside the protected hardware, has never existed outside of that dedicated physical boundary, and is secured against tampering. Google handles the physical security, monitoring, power, and maintenance of the hardware. The customer just manages the key policy and access.
So it's the highest level of security available without requiring the user to physically manage the hardware in their own data center.
It is.
Okay, let's pivot from data at rest to data integrity during transit. We discussed ensuring a human user's identity. What if we need to guarantee non-repudiation proof that a message or a transaction truly came from the claimed user to prevent spoofing?
This requires a digital signature, and you do that by leveraging public key infrastructure, or PKI. The technique is to digitally sign the message client side using the originating user's private key.
I think we need to slow down on this point because it's often confusing. We usually think of encryption as using the public key to protect a message, so only the private key holder can read it. Why are we signing with the private key here?
That's a great question because the goal is not confidentiality. The goal is authentication and integrity. The process is this. The sender takes a hash, a unique mathematical summary of their message. They encrypt that hash using their personal, secret, private key.
And that encrypted hash is the digital signature.
Right. The original message and the signature are sent. The recipient then uses the sender's widely available public key to decrypt the hash. If the public key successfully decrypts the signature, it proves that the signature could have only been created by the owner of the matching private key.
So if confidentiality is like sealing an envelope so only one person can read it, non-repudiation is like applying a cryptographic notary stamp on the outside that proves, mathematically, that only you could have put that stamp there.
Exactly. It guarantees the sender can't later deny having sent the message, which is vital for legal and transactional systems.
Okay, let's wrap this section by moving to the high-level compliance landscape. Compliance and governance requirements. This is where the security rules we've discussed meet the regulatory world.
And compliance is the shared responsibility model in action. Take PCI DSS, the payment card industry data security standard. The cloud provider offers certified infrastructure, but the customer is responsible for building a compliant environment on top of it.
And a common misconception is that you must use a specific platform, like App Engine or something.
Right, but the reality is that any platform, including complex ones like GKE, Google Kubernetes Engine, provides the tools you need. Segmentation, logging, access controls to build a PCI DSS compliant environment. The organization has to implement and audit those controls themselves.
That distinction is crucial. And when dealing with PCI, the number one goal is always minimizing the PCI scope.
Always.
So if you're processing credit card transactions, but your data science team needs to track those transactions for analysis, how do you minimize the number of resources that fall under the stringent PCI audit requirements?
This requires an architectural commitment, and it ties right back to our DLP discussion. The optimal architecture is to create a highly isolated tokenizer service and store only the tokenized data in your analytical environment, like your main BigQuery warehouse.
So only that small, isolated tokenizer service ever touches the raw card numbers.
Exactly. It's Vault. It's data input streams. That's it. Every other component, your microservices, your dashboards, your analysis pipelines, only handle the safe tokens, which can reduce the PCI audit scope by, maybe 90% or more.
That drastically reduces complexity and cost.
Yeah.
Now, briefly on major data sovereignty regulations like GDPR.
Compliance with GDPR is purely an architectural commitment. It's not a button you click in the console. It requires the organization to fundamentally design its application around principles like data minimization, the right to erasure, and purpose limitation.
It forces you to think about where you store the data, how you process it, and when you delete it.
You got it.
Okay, final control point in this section. Deployment integrity. We need to prevent human error or malicious deployment of untested code. How do we ensure that only container images that have been scanned and digitally signed by our QA team can be deployed to production?
That security gate is binary authorization. It inserts itself right into the deployment pipeline, and it acts as a mandatory approval workflow. It verifies that the image carries the necessary digital attestations, the cryptographic proof that it passed security scans, QA checks, or legal sign-offs.
And if the image lacks that valid digital signature?
Binary authorization will block the deployment entirely. It prevents untested code from ever reaching your cluster.
We have built a castle, protected the borders, and secured the treasury. Now we need surveillance. This section is all about achieving necessary visibility and enforcing those high-level, overarching controls that govern the entire organization.
And visibility starts with robust logging, but there's a critical operational distinction here that often trips up new security teams.
Okay, what are the two types of logs we need to worry about?
So the cloud automatically collects all admin activity logs, who changed an IAM policy, who deleted a database, who enabled a new service. This is the activity happening at the control plane level.
Yeah.
However, if you want to collect specific VM system logs, things like operating system events, application crash reports, or standard kernel messages inside the virtual machine, the Stackdriver logging agent must be manually installed and configured on each instance.
So relying solely on the automatic logs means you see the external administrative actions, but you're completely blind to what's happening inside the operational heart of your servers. That agent installation is a necessary operational hygiene step.
It is non-optional for full visibility and forensic analysis. Now, let's talk about operationalizing that log data, particularly for external reviews. Auditors frequently need to review policy changes, often looking back 12 months for compliance checks.
And manually sifting through millions of API calls in a console is paralyzing.
It's impossible. So how do we turn that massive, unwieldy stream of audit data into something structured and queryable? The most efficient process is to enable logging export to Google BigQuery.
Okay, BigQuery.
And then you use access control lists and views to scope the data you share with the auditor. BigQuery is a petabyte-scale data warehouse designed specifically for rapid analytical queries.
So instead of giving the auditor access to the raw logs, which could grant them way too much visibility, we give them access to a structured, queryable table in BigQuery.
Precisely. You create controlled views over the exported data, maybe a view that only shows IAM policy changes over the last year. This provides the auditor with the exact searchable data set they need, allowing them to run complex queries in minutes instead of days.
And you're sure they only see what they're supposed to.
Exactly.
That transforms a dreaded manual task into a simple analytical query. That's a huge efficiency win. Okay, let's move up the hierarchy again, back to the organization level to discuss preventative control setting high-level organizational guardrails.
Right. So if the security team wants to ensure that no IAM user from outside the corporate domain, no personal Gmail accounts, no external contractor domains can ever be granted permissions within the organization's cloud environment, they need a domain-level gatekeeper.
They need a policy that precedes any IAM decisions.
They have to configure an organization policy to restrict identities by domain. This is a powerful hierarchical constraint. It acts as a gatekeeper that applies across the entire hierarchy, folders, projects, and resources, and it prevents any external identity from ever being bound to an IAM role.
So even if a project owner accidentally tries to add an external user,
The organization policy blocks the action, preventing sprawl and a lot of supply chain risks.
that is critical for establishing the corporate boundary of trust. Finally, let's return to our automated systems, the service accounts. For a large, modern, distributed application, say 30 microservices that all need to connect to databases, where should the database credentials live?
The credentials, passwords, API keys, tokens must never, ever be stored in plain text. And that means absolutely no source code, no environment variables, and no configuration files. If any part of that system is compromised, the entire database is exposed.
So what is the single, secure repository for credentials in a large dynamic system?
They must be stored in a secret management system. These are dedicated vaults, which are themselves highly secured and audited, that handle the storage, retrieval, and rotation of credentials.
And the applications request the secret at runtime.
They do, using their service account identity. They present their proof of being a robot, and the vault dispenses the temporary secret. The vault also enforces key rotation policies, ensuring the credentials are automatically updated and expired, which maintains security hygiene without any human intervention.
This has truly been a deep dive into the foundational architecture of cloud security. We started with the basics and covered everything from granular identity management all the way up to the ultimate boundary enforcement.
We've really established the three non-negotiable pillars of this domain. First, the foundational structure, the hierarchy, which defines the which resource, and the vital implications of that union inheritance rule. Getting that right dictates everything else.
Second, we define the identities and access controls, distinguishing between human identities managed by Federation and the service accounts, the necessary robots of the cloud, and, moving away from those broad primitive roles toward fine-grained least privilege.
And finally, we explored the ultimate data protection measures. VPC service controls for establishing that strict security moat around sensitive data to prevent exfiltration, and Cloud DLP for surgically handling PII via redaction and reversible tokenization, all backed by controlled cryptographic infrastructure in KMS.
Yeah. Cloud security, as we've seen, it's less about a single lock and entirely about nested security zones that all have to align perfectly.
Right.
We've spent significant time mapping out how to identify the who the user and how to enforce the where the network context using IAP and access levels. But here is the final thought to consider as you build out or refine your systems. We focused heavily on the auditability of human identities, but the most silent and potent risk often resides with the automated ones.
What happens when the who is a service account, a robot, that suddenly gains overly permissive access because of some forgotten IAM grant on an inherited folder?
Exactly. We know the administrative audit logs are already being exported and operationalized in BigQuery. The next level of challenge isn't just reacting to a breach, but proactively investigating service account risk.
What continuous internal auditing process is required to ensure these non-human identities stick strictly to their job descriptions, especially since they can't be held accountable in the same way a human employee can? That is where truly advanced security investigation begins.
A vital and increasingly relevant question for anyone operating in a multi-service cloud environment. Thank you for guiding us through this necessary deep dive.
My pleasure.
And thank you, the listener, for spending this time with us. We hope you walk away with a clear map of cloud identity and security, equipped to navigate the jargon and establish strong governance in your own environment. Until next time.